Sorry for the delay, but I appreciate the patience most of you have shown. I want us to continue with our discussion of flight in insects. The last bit we did was the action of the direct flight muscles, and we said direct flight muscles, those ones are attached at the base of the wings, right? Take note. Insects that use direct flight muscles, we say those ones have large wings, and their wings are attached. The muscles which support the wing is attached at the base of the wing. And we gave examples of the insects that carry out, that use direct flight muscles as large insects. And we mentioned insects such as the dragonflies, the moth, the butterfly, and the locusts, right? Now, those insects that use the indirect flight muscles, those are muscles which are not attached at the base of the wing, but they are attached to the roof, right? To the roof or to the tagam, right? And similarly, there are also two sets of muscles. We have the depressor muscle and the elevator muscles. So without wasting time, you need to know how those two muscles and those indirect muscles are characteristic of insects that are small in size, the small-sized insects. Those are very active insects. For them to keep in space or in flight, they have to keep moving their wings at a more rapid speed. So they keep flapping rapidly their wings. Using indirect flight muscles, indirect flight muscles are characteristics of insects. Can say indirect flight muscles are characteristic. These are characteristic of insects. They are characteristics of insects with small wings. Insects with smaller wings. We can cite examples of such insects that have small wings and a rapid wing beat, and have a rapid wing beat. They have a rapid wing beat. We can cite examples of such insects as the wasps, the housefly, or houseflies, and the bees. Those insects have small wings or short length wings. The bees, you can also cite the beetles, the dung beetle or the dung roller, the dung beetles. Such insects, their wings are small in size, right? And they are always in rapid motion. So these flight muscles are attached to the walls and roof. Indirect flight muscles, the indirect flight muscles are attached. These muscles are attached to the roof and side walls of the thorax. The side walls of the thorax, but not attached directly to the wing base. Not attached directly to the wing base. They are not directly attached to the wing base. For that reason, that is why they are called indirect flight muscles. because of their attachment to the body and more so to their thorax. So how are these muscles used? Remember, they occur in two pairs. And remember, we said muscles that appear in pairs, they work antagonistically. They bring about opposing effects to one another. As one muscle is contracting, the other muscle is relaxing. So that mode of operation of muscles, where one muscle brings about an opposing effect to the other, is being antagonistic. So the elevator muscles, which raise the wings, the elevator muscles which raise the wings, one of the sets of muscles are the elevator muscles. Those ones are concerned with raising the wings. Are dorsoventrally attached. These ones are dorsoventrally attached. They are dorsoventrally attached. Dorsoventrally meaning dorso is top. So they are attached at the top and on the ventral side, ventral under, top and under. Right? They are dorsoventrally attached. The other set of muscle besides elevator muscle is known as the depressor. The depressor muscles, which lower the wing, the depressor muscle, which lower the wing, are arranged longitudinally. These ones are arranged longitudinally. They are arranged longitudinally. Please you take note of the arrangement and attachment of the indirect flight muscles in such insects. We are talking about those muscles which are not directly attached to the wing base. Remember the direct flight muscles, we said those ones are attached directly at the base of the wing. The indirect flight muscles are attached to the roof and side walls of the thorax, but not attached directly to the wing base. And we are saying there are two muscles there. The elevator muscles, which raise the wings, those ones are attached dorsoventrally, right? Dorsoventrally. Then the depressor muscles, which lower the wing, are arranged longitudinally. Those ones are arranged longitudinally. You can have illustrations of simple drawings to show how those muscles, those two sets of muscles, appear or are positioned in the body of those small insects. Please take note. Indirect flight muscles are characteristic of insects with small wings. They are a characteristic of insects with small wings. And they have a rapid wingy beat. Examples, we have cited the wasps, we have cited the houseflies, we have cited the bees, and we have also given the dung beetle or the dung roller, right? So we need the drawings to show the arrangement and the attachment of those indirect flight muscles in the body of such insects. So the action of indirect flight muscles, like we saw for the direct flight muscles, the mode of action involves two stages. It involves the upstroke, the raising of the wing, and the downstroke, which involves the lowering of the wing. So the position of the wings during upstroke, position of the wing, position of the wing during upstroke, during the upstroke. So the muscles which arise from the roof or the tagum are the ones we call the elevator muscles. Then the ones which are not attached directly to the roof are the ones we are calling the depressor muscles. They lie longitudinally. They are longitudinally arranged. So we have the tagum, which we can refer to as the roof of the thorax. Then we have the wall of the thorax, the wall of the thorax, thoracic wall. So we have the elevator muscle, the elevator muscle in a state of contraction. When they are contracted, then you have the depressor muscle in a state of relaxation. The depressor muscle in a state of relaxation. So that is during upstroke. So during upstroke, we can say, in summary, during upstroke, the following changes occur. So during upstroke, the elevator muscles contract. One, elevator muscles contract. Elevator muscles contract. So in a contracted state, what happens? What's the effect of the elevator muscles contracting? When the elevator muscles are contracted, they bring about an effect to the roof of the thorax or the tagum. They pull against the roof. When they contract, they pull against the roof. They pull against the roof, of the thorax, roof of the thorax, also known as the tagam, also known as the tagam. So when they pull against the roof of the tagam, this brings about moving, which moves downwards. The effect is the tagam is moved downwards. This causes the tagam, to move downwards, I repeat. So during upstroke, when the elevator muscles contract, they pull the tagam, they pull against the tagam, lowering or pushing the tagam downwards. So as the tagam is pulled downwards, remember the attachment of the muscles is on the rooftop of the thorax or the tagam. So pulling down the tagam means raising the wing upwards. Are you together? So elevator muscles, when contracted, they pull against the roof of the thorax or the tagam. So the effect of the elevator muscles pulling against the tagam causes the tagam to move downwards. Then this expands and stretches the depressor muscles. This expands and stretches. It expands and stretches the depressor muscles. 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 And the result is the wing is raised. The result is the wing is raised. The wing is raised. The wing is raised. The wing is raised. Meanwhile, the depressor muscles relax. Meanwhile, the depressor muscles relax. The depressor muscles relax. Meanwhile, the depressor muscles relax. That is the first phase. To lift the wing upwards, elevator muscles contract. When they contract, they pull against the rooftop or the tagam. Pulling the tagam downwards means exerting more pressure on the depressor muscles. So the depressor muscles become expanded and they become more stretched. So the result is the wing is raised and the depressor muscles remain in a relaxed state. That is one stage of using the indirect flight muscles during flight. So the other one is downstroke. The downstroke phase. The downstroke. So position of the wing during upstroke. Now what happens during the downstroke? Downstroke. Position of the wing during downstroke. Downstroke. So the reverse is true. The reverse is true for downstroke. Here's the opposite of this. What has been taking place during upstroke is the opposite for downstroke. So during downstroke, we just change the position of the wing on our drawing. These muscles again change their mode of action. Wing here is now lowered instead of being raised. So here wing During downstroke, the wing is lowered. During downstroke, the elevator muscles relax. Elevator muscles relax. Depressor muscles become contracted. So the depressor muscles contract. So the wing is lowered. Wing is lowered. The wing is lowered. The wing is lowered. The wing becomes lowered. So we can build on that now. During downstroke, as I've said, the opposite is just true for upstroke. So during downstroke, just change. Elevator muscles relax. The elevator muscles relax. The elevator muscles relax. We can say, you can begin with a depressor. So during downstroke, the depressor muscles contract. During downstroke, depressor muscles contract. The depressor muscles contract. So what is the effect of the depressor muscles becoming contracted? When they contract, they pull in a horizontal direction. They pull in a horizontal. They pull in a horizontal direction. They pull in a horizontal direction. This compresses or squeezes the thoracic wall. This compresses or squeezes. This compresses or squeezes the thoracic wall. The thoracic wall or the thorax wall. The wall of the thorax. When they become contracted, they compress the thorax wall. Compression of the thorax wall has an effect on the wing attachment. So the walls become compressed or they become squeezed lengthwise or inwards. Lengthwise or inwards. Lengthwise or inwards. Lengthwise or inwards. This raises the pressure in the thorax. So this raises the pressure in the thorax. It raises the pressure in the thorax. It raises the pressure in the thorax. When pressure is raised in the thorax, the roof or the diaphragm, the roof or the diaphragm, is pushed upwards. Diaphragm is pushed upwards. It is pushed upwards. The roof or diaphragm is pushed upwards. And this brings about lowering the wing. This results in lowering the wing downwards. Results in lowering the wing downwards. Meanwhile, the elevator muscles relax. Meanwhile, the elevator muscles relax. Meanwhile, the elevator muscles relax. Elevator muscles relax. Meanwhile, the elevator muscles relax. This cycle of events is repeated. This cycle of events, this cycle of events, this cycle of events is repeated. The cycle of events is repeated, thereby maintaining the insect in flight. Maintaining the insect in flight. Maintaining the insect in flight. Maintaining the insect in flight or in space. In flight. So, in summary, during downstroke, using the indirect flight muscles, the depressor muscles become contracted. Depressor muscles contract. So the effect of contraction of the depressor muscle is pulling the tagum, right? Sorry, compressing the walls of the thorax. So depressor muscles contract, they pull in a horizontal direction. They pull in a horizontal, pulling horizontally. Horizontally. So they pull in a horizontal direction, compressing. So the effect of pulling in a horizontal direction, it compresses, squeezes the thorax wall. Squeezes the wall of the thorax. Squeezing the wall of the thorax lengthwise or inwards raises pressure on the thorax, or the roof of the tagum. It raises pressure on the roof of the tagum, which is pushed upwards. Is pushed upwards, so the wing is lowered. And as that is happening, the elevator muscles are in a relaxed state. So the cycle of events is repeated from time to time. To change, raise the wing, the reverse is true. To lower the wing, as we have seen for downstroke. It's important to take note of those drawings showing the position of the wings as the insect is in flight. An assignment. Are there questions you're asking? Are there members raising some questions? Any questions? If you have questions, you ask. Any questions? Any comments? Any supplements? Any elaborations?
Sit on the tagum, like when upstroke. And during downstroke, you say no, during upstroke you say the roof of the tagum rises. So during downstroke, like the arrows are still going.
Sorry, thank you for that observation. Someone has observed that the drawing makes some improvement there. I did not remove the arrow. So in this position, I make an improvement here about the shape of the tagum. About the shape of the tagum. Make it somehow curved or dome-shaped. Curved or dome-shaped. The tagum is arched up. The tagum is arched up. So in your drawing, please add that. Add those arrows. Thank you for that observation. Okay. An assignment, or we can make it a discussion for our work, for betterment of our work. So, you can raise a question about adaptations. Adaptations.
Question.
Yes. Someone is asking.
Kasule is saying, do they ask for the whole process in exams?
Kasule is asking something that the process of flight seems Kasule are worried. Yes, they do. Yes, the question. If you have a question bank, Kasule, I implore you and encourage you to refer to your question bank, the UNEP question bank. You'll find many questions about flight in insects using either direct or indirect flight muscles. So you have to know. It's something simple, Kasule. Don't get worried. Just get to know as you are reading through your notes. Get to know the attachment of these muscles. If I'm talking about direct flight muscles, where those ones are attached at the base of the wing. Are you together? Those ones are attached at the base of the wing. They are directly at their base. That's why they are called direct flight muscles, because they have a strong attachment to the wing. The ones called indirect flight muscles, the ones we have just discussed today, right? Those ones are not attached directly to the base. Where are they attached? To the roof, right? To the roof. And those that appear longitudinally. Are you together? Please carefully revise slowly. You'll get to know the whole process. The whole process is examinable, please. So my concern is about adaptations. Can ask you a question about adaptations of insects for flight. How are insects adapted for flight? How are insects adapted for flight? Question. Outline the adaptations. Outline the adaptations of insects. Adaptations of insects to flight. To flight. How are they adapted to flight? Now we have been talking about muscles. So one of the unique and important characteristic feature for flight in insects are the well-developed muscles. You can say one, they have well-developed flight muscles. Well-developed flight muscles. Well-developed flight muscles. But put in mind that we are talking about either indirect flight muscles or direct flight muscles. Well-developed flight muscles which aid the insect, to keep in space or in flight. That is one. Another adaptation, remember as we are stating adaptation, you mentioned the feature. The feature is flight muscles. Please you take note. Relate the feature to the function. Flight muscles that are well developed. They keep the insect in space. They keep it in flight, in motion. Then the other adaptation, you can say they have an exoskeleton. They have an exoskeleton. We have been talking about the tagam and the wall of the thorax. An exoskeleton which provides surface for attachment of the flight muscles. Attachment for the flight muscles. Attachment for the flight muscles. Attachment for the flight muscles. The exoskeleton, we are talking about the tagam and the thoracic wall. They provide surface for muscle attachment. That is a very important characteristic feature. Another adaptation insects have, they have wings. Well developed wings. well-developed wings. Remember we talked about those that use direct flight muscles, and the examples we cited are the insects that have large wings. We gave examples of the dragonflies. We gave examples of the moth. We gave examples of the locusts. So in such insects, their wings are large. However, today we have talked about those that have small wings, right? But they are able to fly as well. They have well-developed wings. Well-developed wings, which increase, surface area, which increase surface area for flight, for flight, for flight, for flight. So take note. This could be a possible question. Outline the adaptations of insects for flight. Adaptations of insects for flight. Adaptations of insects for flight. Another one. Now remember, these insects move in space. They swim or float in space in air. You can also cite another one. If you look at their body shape, it's about their body shape. So you can describe their body shape as being, right? You can say they have a streamlined body shape. Having a streamlined body shape. They have a streamlined body shape to minimize air resistance during flight. To minimize air resistance. Minimize air resistance during flight. To minimize air resistance during flight. They have a streamlined body shape to minimize air resistances during flight. During flight. Okay. So that is about locomotion in insects. Remember where we started from? About locomotion in insects. We said some insects can walk. They have walking legs. Other insects have wings. We talked about how they use the legs to walk. Like we have also seen the wings and the muscles that cause the wings to be raised or lowered. The legs also, we talked about muscles of the leg. Now today we have talked about the muscles of the wings. Then the other one maybe you can also cite, and under the adaptations, insects have well-developed compound eyes, right? The compound eyes enable the insect to dodge obstacles and make correct judgments of the landing distances for landing. Hardly do they collide. Hardly do they damage their bodies, their wings, because they are unable to see. But because of the size of their compound eyes, they are well positioned on the head. Remember, they can be described as dorsal, right? They lie on top and on the sides. They are dorsolaterally positioned. So they have compound eyes which are dorsolaterally positioned on the head. Dorsolaterally positioned on the head. Positioned on the head. Dorsolaterally positioned on the head. So because of that, they are able to dodge or avoid obstacles. You never see them colliding with walls or with the trees. And they can use their eyes to make good judgments when landing, correct judgments of landing distances. They don't just fall like a luggage, right? But they are able to land safely on the ground without any harm or any damage of their body. So that is a possible question they can raise about adaptations, special adaptations of insects to flight, having well-developed flight muscles. At the back of your mind, get to know which muscles are they talking about. The depressor, elevator. In both cases, whether direct flight muscles or indirect flight muscles, the name remain elevator, depressor. But the difference is where other muscles are attached. If we talk of direct flight muscles, get to remember those are muscles attached at the base of the wing. Indirect flight muscles are attached to the roof and horizontally, right? Or to the walls of the thorax. As simple as that. Let us look at locomotion in another organism. I want us to move to locomotion in fish. Or before fish, can we look at locomotion in birds? Locomotion in birds. Locomotion in birds. How birds are able to move. Locomotion in birds. So we can look at that one. Hope all of you have the notes and have been copying the notes well. You could be missing the drawings. We shall be adding the drawings as we carry on with that discussion of the different modes of locomotion in different organisms. So we look at locomotion in birds. Locomotion in birds. Locomotion in birds. Locomotion in birds. There are many different types of birds. Like we saw for the insects, there are those birds which can walk. There are those birds which can fly. There are those birds that are unable even to lift their bodies off the ground completely. So birds can run, can swim, and fly. So modes of locomotion. Can say modes of locomotion in birds. The modes of locomotion in birds. The modes of locomotion in birds. You can cite one, flight. That is one mode of locomotion. They can fly. Swimming. We have swimming birds. Swimming. Then we can have the walking birds. Or those that can run. Walking, or running. Those are three main modes of locomotion in birds. There are those that can fly, lift their bodies off the ground, and move high in the sky. There are those that are good at swimming. They move in water, right? They move in water. You may not say that they are basically aquatic. They are partially aquatic. They go into water maybe to look for food or clean their bodies, right? Sometimes they move in water, especially those that want to get rid of the parasites in their feathers. They go in water for that reason, right? Some parasites are uncomfortable with water, right? So they use water as a means of cleaning off parasites from their feathers, right? Or even to clean their bodies. And those ones are good at swimming. Examples of those that can swim. We have members in the duck family. The ducks. Those ones can swim in water because they have webbed feet. They have webbed feet. They have webbed feet. There are those that entirely walk throughout their life. They are unable to lift their bodies. Examples here we can give the ostrich, the kiwi, right? Emu, good. Someone is giving emu. Yanis has mentioned emu, ostrich, kiwi, emu. Those ones can walk. However, the most characteristic form of locomotion in birds is by flight, right? So, however, the most common mode of locomotion, in birds, common mode of locomotion in birds is by flight. The most common mode of locomotion is by flight. So most birds have power of flight. Then in birds, the forelimbs are modified into wings. Take note. The forelimbs are modified into wings. They are modified into wings. And their skin is covered with feathers. And their skin is covered with feathers. The wings have a very large surface area and have very little weight. The wings have a very large surface area with very little weight. That is a special adaptation, or those are two special adaptations, right? Forelimbs being modified into wings, right? Skin covered with feathers. You take note, wings being large, providing a large surface area. Wings being very light in weight, right? Reduces the weight, the bulkiness of the body of the bird, so as it can have less weight or burden, right, when in space. Then, some few examples of birds have both wings and feathers but are unable to or cannot fly. And we have cited some of those birds which are unable to fly. Flightless birds. The flightless birds, we have given examples of the kiwi, the ostrich, the emus. So locomotion in such birds, we have said it's either by running or walking. Some can even go in water and swim, right? Some can go in water and swim. So at that point, I want us to add on adaptations. Adaptations of birds for movements in air. Adaptations of birds for movements in air by flight. Adaptations of birds for movements in air. Movement in air by flight. Movement in air by flight. Adaptations of bats. Like we have already mentioned, the feathers play a very key role in flight, and their attachment and arrangement on the body, they are backward pointing. So being backward pointing means they lie or they provide that streamlining of the body. They don't counteract any air resistance when in flight. Then we have also said that is a modification. You have said the forelimbs are modified into wings, right? In some birds, the wings are very large. There are even small birds, right? Like the ladybirds, like the weaver birds, their wings are smaller. But if you look at big birds like the ostrich, the marble storks, the eagle, their wings are big in size. The vultures, those scavenger birds, their wings are large. So, about adaptations, you can mention one, forward limbs. The forward limbs are modified into wings. Are modified into wings. They are modified into wings with the feathers. With feathers which provide a large surface area for flight. Which provide a large surface area for flight. Which provide a large surface area for flight. Then the endoskeleton is made up of small hollow bones. Birds have an endoskeleton. They have an endoskeleton made up of small hollow bones. Small hollow bones. Endoskeleton made up of small hollow bones. When you talk of a hollow bone, many of you that eat birds, I believe all of us eat birds, right? And we enjoy birds, not so? You know, when you talk of birds, people think of only the wild birds. But we eat birds, we eat the chicken, we eat the ducks, we eat those edible birds. So if you eat those birds and you take note of their bones, there is space within the bone, right? That is what we are describing as being hollow. So the advantage of having a hollow bone means less weight. The burden of carrying a lot of luggage or mass in space is minimized by having hollow bones. Their bones are not compact, so there is less weight when the bird is in space. So they have small hollow bones which make it light. Which make it light to easily be carried in space. To be easily carried in space. To easily be carried in space. Another one, their bodies are streamlined. Their bodies are streamlined. They have a streamlined body shape. Their bodies are streamlined. Their bodies are streamlined in shape, which reduces air resistance during flight. Streamlined in shape, which reduces air resistance during flight. Air resistance during flight. Please, you take note. We mentioned the adaptive feature as streamlined body. That is the feature. Related to the function. Being streamlined reduces air resistance. That is how you score a mark. Right? That is how you score a mark. State adaptation to the function. Adaptation to the function. The feature to the function. Number 3 or number 4, can say birds have a rigid and firm skeleton. That rigid and firm endoskeleton. Rigid and firm endoskeleton. They have a rigid and firm endoskeleton for providing surface for attachment of the flight muscles, right? Made up of many fused bones, made up of many fused bonds, made up of many fused bonds, which provides a firm framework for attachment of flight muscles, which provides a firm framework for attachment of flight muscles. Attachment of flight muscles. Okay. Those are 4 adaptations. 5. They have large and powerful flight muscles. Birds have large and powerful flight muscles. Large and powerful flight muscles. These flight muscles in birds have a general name, pectoral muscles. The pectoral muscles. Take note. They have a general name, pectoral muscles. These muscles are large in size and they are powerful. So they have a general name, pectoral muscles, but they occur in a pair. So we have the pectoralis major and the pectoralis minor. So they have large and powerful flight muscles, the pectoral muscles, for flapping or depressing the wings. For flapping or depressing, flapping and depressing the wing during flight. For flapping or depressing the wing during flight. Number 6, birds have a large sternum, or you can call it a breastbone. Birds have a large sternum. They have a large sternum. Call it breastbone. A breastbone. They have a large sternum or breastbone with a deep keel. Which provides a large surface area for attachment of flight muscles. Which provides a large surface area for attachment of the flight muscles. Attachment of the flight muscles. Okay, let us finish up these adaptations. We have about 5 minutes to go. They have a keen sense of sight. Another adaptation, they have a keen sense of sight. Remember, we talked of good visual acuity in the insects. Similarly, these birds have a very keen and a stronger eyesight. they have a stronger eyesight or a very keen eyesight. They have a very keen eyesight. They have a very keen eyesight to make good judgments during landing and avoiding obstacles. Keen eyesight. Keen eyesight to dodge obstacles, to avoid colliding with obstacles, dodge obstacles, and make good judgments. Good judgments on landing. On landing. It is to the advantage of the bird, the eye to dodge the obstacles when in flight, and the eye to see where it's going to land, the surface where it's going to land. It doesn't just fall like a luggage, because if that is to happen, it's likely to damage the feet. But because of that strong eyesight, can make correct and good landing judgment. Then they have lungs with numerous air sacs. They have lungs with numerous air sacs. Numerous air sacs. Air sacs. Their lungs have extra bags, extra air bags, right? Their lungs have extra air bags, which provide more surface for gaseous exchange. Numerous air sacs which increase surface area for gaseous exchange. Surface area for gaseous exchange. Their lungs have numerous air sacs for storage of extra air and for providing more surface where gas exchange can take place. Another adaptation, they have a high metabolic rate. Birds have a high metabolic rate. They have a high metabolic rate. Now, having a very high metabolic rate means there is increased production of energy. So this assures the birds of more energy, provides more energy for the birds when in flight. When in flight, and even that high metabolic rate increases on heat in the body, thereby regulating the body temperature of the bird, right? Remember, it is an endotherm. It can generate own body heat. Then they have a very efficient blood circulatory system. They have an efficient blood circulatory system. Efficient blood circulatory system. Circulatory system which rapidly distributes metabolites for respiration. Metabolites for respiration, like food material to the actively respiring muscle cells during flight. Then another adaptation, they have a high red blood cell count. They have a high red blood cell count. Red blood cell count. They have very many red blood cells or erythrocytes for rapid transportation of oxygen. For rapid transportation of oxygen, rapid transportation of oxygen to actively respiring muscle cells. Actively to respiring muscle cells. Remember, for it to fly, it keeps flapping the wings. So it needs energy. So for that reason, it has many red blood cells for transporting of oxygen to respiring muscles. Then some birds or their red blood cells contain a pigment called myoglobin. Their red blood cells contain a pigment called myoglobin. Myoglobin, which has a higher affinity for oxygen. A higher affinity for oxygen. So because of time, let us stop here for today. We shall continue with our discussion of locomotion in birds. So we have looked at locomotion in insects, and we have had an introduction to locomotion in birds. So I wish you the best and I encourage you to keep safe at home. Yes. How are you?